Hi, I'm Alex Lamb, author of the Roboteer science fiction novels, and you're watching Secrets of the Universe, the thrilling video sequence in which I attempt to, in effect, improvise my way through all of science communication, covering one massively weighty topic for a video and communicating pure, unadulterated truth, give or take a few bursts of complete and utter nonsense because I don't really know exactly what it is that I'm talking about. But enough of that. What are we going to talk about today? Today we're going to talk about the origin of all life. A simple little topic, ladies and gentlemen, which you should be able to cover in 10 minutes or less. So, what is life? I went and looked on Wikipedia to find out. There are apparently 7 properties of a living thing, and I even invented a little mental acronym thing by which to remember them, and that is HOMGAR, the tremendously alive barbarian. So what does HOMGAR stands for? Well, homeostasis. In other words, a living system is one that sort of like keeps itself in balance. Organization, it's got a shape, if you like. Metabolism, energy comes in and stuff is changed. G, growth. Growth is, it has size changes. A, adaptation to its environment. R, reproduction, and R, again, response to stimuli. So there we go. There are the 7 exciting things a living system is supposed to do. But somehow we got there from molecules. We got there from just just sludge sitting around on a dead planet. How did this possibly come about? An intensely fascinating subject, ladies and gentlemen. Everybody wants to know where they came from, don't they? We've been built countless belief systems built on enormous towers of purest nonsense trying to answer this question. So let's delve deep into the science of it and see if we can unpack it. Well, there are about, I would say, 3 really good theories that have come about trying to explain abiogenesis, as they refer to it. One is the replicator molecule model, in which life starts because somewhere in the primordial soup on the surface or down near an ocean vent, a molecule shows up that has the ability to reproduce itself and then make more of itself. And then once you start with a very simple molecule, it goes on and there's a sort of a chain reaction, if you like, and then from that life springs. It's pretty popular as an idea. I'm not a big fan. And the reason why I'm not a big fan is because when I have looked at systems of this sort, the thing about self-replicators is, despite the fact that they're tremendously good at making more of themselves, there's also a locked-in system, if you like. The incentives in the environment for a single replicator to get any more complicated are essentially net zero. So a really effective replicator molecule is one that doesn't change at all and isn't subject to any kind of mutative pressures. And when you start off with molecules as large as they were at the beginning of life, which is really just a bunch of little atoms, 200 or 100 or 50 or 12 or whatever, it's very hard to get the kind of diversity and the kind of exciting processes that we see in life. You're more likely to get a chain reaction that goes and expands across the petri dish, or the little sort of tide pool in which its fuel is there, and then basically it gets baked by the sun and all the molecules break, or rain comes down and the whole thing gets washed away in the end. It's not impossible, ladies and gents, but replicator molecules feels too simple and feels too much framed in terms of the biology of larger living systems rather than the chemistry of the prebiotic soup. One that I like a lot more is the idea of autocatalytic sets, pioneered by a chap called Stuart Kauffman. Fantastic fellow, a kind of sort of iconoclastic complex systems titan who made up many exciting things. What is an autocatalytic set? Well, an autocatalytic set is a bunch of little molecules that help in the production of each other. So molecule A traps things in its environment and sort of makes more of molecule B. Molecule B is made by A. It doesn't care much about A, but it spends a bunch of time catalyzing the production of C, and then C happens to do the same process to catalyze the production of A, if you like. And so between them, A, B, and C together create a cumulative effect. And so if you have an environment that's got a bunch of different stuff in it, as soon as you get a cycle of A, B, and C, they're able to sort of produce more of themselves. Now, any one of these catalytic cycles is less stable than your sort of replicator molecule from the first theory. However, there are more, if you like, entry points into the cycle of sort of mutual creation that's happening. So that means that once one of these things starts off, the possibility of it being tricked up and becoming more complex over time is much higher. So in that point, you've got, if you like, sort of 3 potential entry points into the system instead of 1. So lower probability of starting, much higher probability of interesting mutation. And it also brings in a very, very important symmetry of life right at the get-go. The prisoner's dilemma, which I described in a previous video. The prisoner's dilemma being, if you like, the symmetry that defines all cooperation. If you have elements in a catalytic set, by definition, if you like, they're all cooperating in each other's production. And that pattern of cooperation appears to be vitally important for all symmetries and all patterns of life that come later. So quite like that one. There's another pattern which I think is potentially even stronger, really very interesting theory, and that is what you might think of as spontaneous encapsulation, to give it a random name that the original scientists didn't, and which they probably wouldn't necessarily be particularly happy with. But we'll call it that. Spontaneous encapsulation, ladies and gentlemen, that's now a thing. What does that mean? Well, early on in the sort of like blobby tide pools in the early Earth, there were certain kinds of molecules that did spontaneously show up naturally in relatively high abundance, and that's stuff called lipids. Or things that do similar jobs to lipids. And lipids are funny molecules that have a kind of a watery connector on one end and an oily connector on the other. And they sort of sit there with their oily connector and their water connector. And what they do is they tend to make little membranes and sort of layers and stuff like this, little sort of sheets and things that can wrap round and form bubbles. So it was entirely possible in the early Earth for there to be tide pools in which you were getting self-enclosed little blobs of chemistry, just purely by virtue of the chemistry of the environment. And these blobs would be formed, and then they would break, and then they would did you get more blobs, and then they would break again. And because the level of water in these tide pools was constantly rising and falling, the sun was shining down, and there was less sun, and there was rain, and so on and so forth. You go periodic breaking and formation of blobs. What's really important about blobs is that they provide, if you like, areas in which specialized chemistry can start to happen. Now, even though that specialized chemistry isn't itself necessarily alive, you've done something wonderful the moment you've created these blobs, and that is you've created what's called a loosely coupled system. Now, the conditions for prisoner's dilemma, the symmetry that defines all of cooperation, really likes a loosely coupled system. The best way to get cooperation to happen is to run what's called an iterated prisoner's dilemma game, in which you have certain partners who are trying to be cooperating or not, but basically you trap them in a room together. They have to learn to get along, and then you take them out of the room, and then you trap some more people in a different room. If you think about it, that was exactly the process that was potentially happening on the early Earth. And what that means is that the environment that might have spurred even the creation of autocatalytic sets was right there, latent in the physical environment, right from the get-go. Marvelous. Now, of course, I've only just touched the very, very surface of what happens with the beginning of life. We can go so much deeper, ladies and gents, particularly because I personally have, of course, you'll be unsurprised to hear, I've tried to make some. Yes, I've tried to make life myself in my own computer lab using the agent-based models that I talked about in previous videos. Yes, you too can make life. So this video probably deserves a follow-up in which what I should do is go into zero-player game mode and talk about how I went about creating life from scratch. Have I covered all of the features of HOMGAR, all the different rules for creation of life? Well, I cover at least 5 out of 7 of them, and And what's more, the simulation will run fast enough that you can watch it happen in real time. And you can watch the formulation, if you like, of sort of self-stabilizing, artificial living things in a computer simulation swim around and try and eat each other and things like that. And how did I do that? I did that by, if you like, a form of sort of physics, biology, sort of symmetry cheating. But we'll explain how that works in a later video. For the time being, that's probably enough for now. Homgar, ladies and gentlemen, and the origin of life. You've heard the story now. Which of these three exciting theories do you think is correct? Replicators, autocatalytic sets, or spontaneous encapsulation? I think it's likely one of the three. My money's on 3 with a heavy dose of 2. Interested in opinions? Thoughts in the comments. I love you, ladies and gentlemen. You're beautiful people. See you again soon.